Well, good afternoon, everyone. Welcome to Strategies to Lower CO2 Emissions Using Concrete Masonry. On behalf of the Boston Society for Architecture, thank you for joining us today. This event is accompanying the physical exhibition, Durable, Sustainable Material Ecologies, Assemblies, and Cultures, which considers building materials and their impacts as a way to demonstrate that design for durability is an important aspect of a sustainable future. I'm David Fannin. I'm an assistant professor at Northeastern University School of Architecture, and I curated the Durable exhibition at BSA Space with my colleagues Michelle LeBoy and Peter Wiederspan. I hope many of you had the chance to visit the exhibit in person before the pandemic closed the physical gallery. And whether you did or not, I hope that you will check out the digital version, which is on the BSA website. It has many photos of the exhibit as well as a bunch of special insights and behind the scenes looks, videos, audio clips, and articles from the team that put the exhibit together. So you can not only learn more about those topics, but how we put them together. And I'm especially pleased today to be moderating this discussion and to introduce our speaker, Heidi Jandres, who's the Technical Resource and Sustainability Manager at Jandres Block. Heidi provides, in that position, technical and design services for the company. She's part of the third generation of Jandres Block, which is a family business, and she grew up immersed in all of the things related to concrete masonry and has worked as a welder and at the plant prior to receiving an architecture degree from Pratt Institute in Brooklyn. Her work at Jandres and leadership in various industry associations and working groups has advanced sustainability of concrete masonry nationwide. And on a more personal note, I'm really delighted that Heidi has brought all of her knowledge and experiences to Northeastern, where she's currently pursuing a master's degree in sustainable building systems. So as we jump into the presentation, I just want to take a few slides to acknowledge the sponsors for the exhibit and for this event. Our lead sponsor, Spalding, and contributing sponsor, Goody Clancy, and our extensive list of supporters, and also some in-kind supporters. We're very grateful to all of these sponsors for their continuing support of the exhibit and in making this information available. And now as we transition to the credit-bearing portion of the presentation, some kind of standard logistics about the program. There's one learning unit of health, safety, and welfare AIA continuing education credit available. If you keep an eye on the chat, there'll be a link to a Google form. What you need to do is add your name, email address, and AIA number to that form. If you're not an AIA number or you want a certificate, please make sure your name and information, including your email address, are added to that form. We'll be recording this session and it'll be posted to the BSA website at architects.org, and that should be up later this week. And finally, as the presentation is going on, and then when we get to the Q&A session, if you could use the Q&A functions in the chat window, and I'll collect those questions and pass them along to the speaker. That way we won't lose track of anybody's questions or disrupt the flow. So with all of that, I'm happy to hand it over to Heidi, and let's begin.
All right. Hi, everyone. Thank you, David, for introducing. So I am Heidi Jandres from Jandres Block. We've been known for over the years as A. Jandres and Sons. We've reached our 100th year anniversary in 2020, and we are changing our name to Jandres Block, so we don't have to be and sons and granddaughters, which would be me, and then we got great grandsons coming up. So we just figured we'd cut it off and be called Jandres Block. This presentation covers strategies to lower CO2 emissions using concrete masonry. We are part of Concrete Products Group, which is a group of smaller manufacturers like ourselves that have gotten together to have a consistent national product and also pool resources for research and development. For learning objectives, we're going to identify the aesthetic and performance options available with various concrete masonry envelope assemblies. We're going to look at the carbon cycle and how human activity contributes to climate change and discuss different projection scenarios and mitigation strategies. For the third one, we're going to understand how concrete masonry can help build resilient, durable communities and lower operational carbon by utilizing thermal mass. And lastly, we're going to understand the difference between dry cast and wet cast masonry and why this changes CO2 sequestration and how to lower embodied carbon by increasing the sequestration while lowering cement usage. So for an agenda, we're going to do a concrete masonry overview. We're going to look at carbon sequestration. We're going to look at greenhouse gases and climate change, and then on to solutions, and then some updates to the current concrete products, product category rules. So for the overview, there's two types of concrete masonry. We have what we call gray block, which is structural, it's durable, it's very resilient, it's got a really high thermal mass, it's used for firewalls due to it being non-combustible, and it's also a commodity product. On the other side, we have architectural CMU, which is also structural, durable, resilience, has thermal mass used for firewalls, but it's also very beautiful. It can be used both structural and veneers. We do a lot of anchored veneers with veneers. We use specialized aggregates for texture and color that come from all over the Northeast. And we can do multiple finishes and colors. So just a couple of the aesthetic options. We have what we call a smooth integrally colored unit. And in this case, it's a half-high unit, and it juts in and out to create this pattern in the walls. Similar integrally colored unit, which has the look of brick with economy of block. We have our kind of traditional split face. It's been around a long time. And in this case, it's used in banding with a ground face block. Our ground face units can create these patterns using different color schemes. Polish block, which seems to be a new product, but we've been doing it for a little over 10 years now. Time flies, and this finishing process is actually the same process that's used on marble and granite, and it's been customized to use with concrete block. Similar process is a textured polish, where it polishes the aggregate, but it kind of almost scoops out the concrete matrix below it, so it gives us kind of a leathery kind of texture to it. For the different types of wall types, we have multi-wide cavity wall, block backup, either brick or CMU veneer. Here we can utilize the thermal mass, which is on the inside of the insulation. There's also pre-insulated single-wide walls, where the block configuration is actually changed to reduce thermal bridging with the webs between the face shells, and we can also fit enough insulation in there to keep current with energy codes. And also we have our anchored veneer, where it's just veneer units, usually on a steel backup. So now we're going to talk about carbon sequestration, what it is and why it happens, and the difference between dry cast and wet cast, and how this affects carbon sequestration rates. So carbon sequestration, aka carbonation, as it's been known in the industry throughout history. So why does it happen? When cement is produced, it releases CO2. And the main reason for this is it takes limestone out of quarries. It's then heated up really hot to about 2,000 degrees, and this heat causes a chemical reaction. For quick and easy numbers, about 45% of the CO2 released for cement production is due to the energy required to heat it up. And 45% of it is due to the chemical reaction, where the limestone is broken apart, where CO2 is released. What's left is CaOH, or calcium hydroxide, which is also called clinker. This clinker, shown here in these little nuggets, they're about 1 to 2 inches around, get ground up very finely, and that's what our cement powder is. Again, for quick and easy numbers, approximately 45% of CO2 released is due to this chemical reaction. So when water and aggregates are added to the cement, hydration occurs. And from the moment the concrete's produced, it begins this reverse chemical reaction, and the originally released CO2 begins to sequester from the atmosphere. The sequestered CO2 is combined permanently back into the matrix of the concrete as limestone within the concrete. This has historically been called carbonation, and it's part of the reason that concrete shrinks. 40 to 50 years ago, it was studied due to corrosion issues with rebar, because as the concrete carbonates, its pH decreases. But since then, the building codes have kind of figured out, for the most part, corrosion requirements, and the building codes haven't changed for about the past 50 years on this. So some of the similarities between dry cast and wet cast. These are some curves. On the left, we have wet cast. On the right's dry cast. You'd never be able to tell the difference by looking at it. So some of the similarities are the raw materials. They're basically the same. A concrete block production uses different gradation of aggregates than poured concrete, and in different proportions, but the raw materials are the same. So where it's different, the CMU industry on average uses less cement than wet cast. This is due to the manufacturing process. We don't rely as heavily on cement alone to gain our strengths. We use compaction and vibration with machinery. On average, CMU uses anywhere from 6 to 12% cement to aggregate ratio, and ready mix is somewhere around 12 to 15. And I'm using the terms, I just realized I'm using the terms wet cast, poured in place, and ready mix all interchangeably. They're all kind of the same thing. I think ready mix is probably the Kleenex of concrete. So I will try my best to use wet cast. So again, some of the differences, I talked about the machining. Here is our block machine. And here we use a zero slump concrete. So we use very little water, and we use this compaction process. Sorry, that didn't work. So we use a compaction process. So if I were to actually go up to these blocks and grab onto them, they would crumble in my hands. So this is zero slump, and they hold their shape. Now, this opposed to a wet cast, where I'm going to show a slump test here, where it's one of the properties is the different side, the different slumps. So this is a much wetter mix, and so that is one of the main differences. So what does this actually mean? Another one of the differences is we use kilns. Right when it comes out of the machine, we have our blocks holding their shape. We put them into the kilns. Now, the main purpose of the kilns is not so much to heat them up hot. It's really only about 135 degrees. But the main purpose is to keep a consistent temperature and moisture content within the kilns, and it jump starts the hydration process. Moisture content is important for color consistency, and it doesn't get that hot, but it also uses the 50% of the energy for these kilns is generated by the natural heat of hydration, which is given off by the block. So that is another one of the major differences. So due to the CMU being dry cast, it has a more porous structure when compared to wet cast. On the left, we have a zoomed in image of dry cast, which shows the interconnected void structure. This allows some air to penetrate the CMU, which enhances the ability of the block to sequester CO2 throughout the entire block. Not all CMU have this exact structure. Some are more dense, some are less dense. On the right, we have a wet cast with air entrainment. So you can see the little bubbles caused by the air entrainment admixture. This is a much more dense structure, and the air pockets are closed off from one another. So this is why poured concrete primarily sequesters on the outer few millimeters on the outside, which are exposed to the atmosphere. So due to this structure of dry cast and it being more porous, there's absorption limits required by ASTM C90, which are maximum amounts of water that the CMU can absorb and still be considered a C90 block. So as long as the unit conforms to C90 and proper flashing and weeps and crack control are detailed, moisture won't be an issue with your structure. For exterior applications, we always recommend using an integral water repellent. This is an admixture that's added into the mixer while the block's being manufactured. It's not a coating. And this should always be put into the mortar as well. So just a couple of tests here. This is a water droplet test. The block on the right has integral water repellent, and about 2 to 5 milliliter droplets of water are placed on it when it's lying in a horizontal position. Now, it passes if the water sits on top, and this water was sitting on top of this block on the right probably for about 4 hours before I left it and kind of pulled the test. And this block has integral water repellent. On the left is a block that does not have integral water repellent, and you pretty much just suck that water up immediately, like like you could see it just seeping right into it. So this is a good testament on how effective integral water repellent is in the concrete mix. Another test is the ASTM E514 test, which is a spray bar test. This can be done on a sample panel, as shown here, or an individual block. This test is to show water repellency of different CMU units. So on the other side of these panels, on the right side, these units didn't have any integral water repellent, and on the left they did. So it really shows, again, how integral water repellent helps the units repel water. So back to that porous structure. Because of this porous structure, we do need additional measures to control water, but that surface area and void structure produces kind of a carbon dioxide sponge, which is different with dry cast than wet cast. So this is an image of a phenolphthalein indicator solution test. If the indicator turns purple, the pH is above 8.6%. Sorry, the pH is above 8.6. Where the solution remains colorless, the pH of the concrete is below 8.6, suggesting carbonation. A fully carbonated paste has a pH of around 8.4. The rate of carbonation in wet cast is slow. The average rate is about 0.4 millimeters per year, and it slows with age. The wet cast on the right is somewhere around 6 years old, and the carbonation is shown only on the outer crust of the concrete. Until recently, the concrete masonry industry has assumed that CMU would carbonate at the same rate. However, recent testing is showing otherwise. The block on the left is a face shell of a concrete block, and it's about 2 months old. You can see that the carbonation is occurring into the concrete and not just at the surface. And it's also happening at a much more rapid pace. So here are a couple of samples. On the left, we have sample A, which is that 6-week-old sample we just looked at. On the right is our two 20-year-old plus samples. One was out in the yard exposed to the weather for at least 20 years. The other one was above the block machine. It was actually shelving in a shelving unit up there, and that had been there for at least 20 years as well, probably much longer. So we had a lab perform the phenolphthalein test on 3 different blocks. And you can see that on the left, it's starting to carbonate in through, but there's still some areas that are not carbonated at 6 weeks. Now, this gives a good image of what's happening with carbonation, but it doesn't actually give us percentages or any kind of real data. Though there are proprietary carbon sequestration tests out there, our industry is currently looking to develop an industry-wide test method. So one of the current test methods under development is a thermogravimetrical analysis, or it's called TGA. For TGA testing, the concrete is ground up extremely fine and it's heated. So its different substances burn off at different temperatures, and the weight is continuously measured. So carbon burns off at a range of 550 to 900 degrees centigrade. And before it hits this range, it's measured, and then after it's measured. So this is done with all of the raw materials, first off, and then it is done with the block. And in this case, it was done at 6 weeks. And so we can see the difference in carbon content, and that gives us a carbon sequestration rate. So it's currently, the industry is currently looking at TGA testing to figure out if it's a viable test method. So this here is just preliminary testing that I had done. And the sample A on the left shows sequestration rates at a range of 13 to 17% at 6 weeks. And the 20+ block is fully carbonated, and it shows sequestration rates of 25 to 28. And I just want to make a note here about the potential carbon given off due to chemical reaction is roughly around 45. So we're at 25 to 28, where the most we can possibly get is 45. This here, here again is our 6-week sample. Over here on the right, I just got this in, I think it was 2 days ago, and this is the same block at 4 months. And you can see from where the purple is that it's starting to go in a bit deeper. So it's happening much quicker than we previously thought in the industry, which is really, so we're kind of like right at the cutting edge of all of this kind of stuff right now. I have yet to get the TGA testing on this one, but clearly it would seem as it's going to be higher than the one on the left. So going back to that 45-45. And these are very, very rough numbers, but just for the sake of argument, 45% of the CO2 emissions is due to heating, 45 due to the chemical reaction of the limestone breaking apart. You know, I think we can call 10% to other processes, you know, manufacturing processes. So I'm going to focus here on this chemical reaction part, because over here, no matter how much it sequesters, we're never going to change what this is. However, in recent years, cement plants have been starting to become more efficient. In one sustainability report published in 2019 from Heidelberg Cement, they actually report a reduction in CO2 emissions by 22% since 1990. So this is changing, and it is being reflected in the cement PCR. So this here is our sample A at 6 weeks, showing us 13 to 17% of the sequestered CO2. And this fully carbonated is at 25 to 28%. So what about that remaining potential? This is another area of study on how to get the most sequestration possible. And we can do this by changing the way we manufacture, what raw materials we use. And we are looking at this at 28 days and beyond. So, which brings us to new technologies that we've been working with and researching that allow us for improvements in manufacturing with the purpose of lowering cement content and also increasing the sequestration rates. So, why 28 days? This, first of all, it'd be considered to be cradle to gate, which is what our current PCR covers. Our EPDs are cradle to gate. But again, 28 days, because that is a pretty good estimation of when the block leaves our plant. And after it leaves our plant, we really have no control over what happens to it. I mean, does it get put in the ground? Does it get covered up with non-breathable cement, insulation, air barriers? So we really have no way to control it after 28 days, even though we know that if it's left in the environment, it will continue to carbonate. So one of the technologies we've been working on increases the reactivity of the cement we use. It allows us to lower cement and also increases the sequestration rates. Another technology that's out there is injecting CO2 into the mixer during the manufacturing process. And I'm going to talk a little bit more about these technologies a little bit later in the presentation. So greenhouse gases and climate change. We're going to talk about the carbon cycle. So major carbon reserves, I mean, most of the carbon reserves on Earth are in the rocks, 66 million gigatons. And this includes fossil fuels, it includes, rocks, limestone, all of that. And a very small amount is actually, with vegetation in the atmosphere. So the slow carbon cycle is with sediments and rocks, where it's released into the environment. And then it kind of goes into its CO2 is pulled out, mixes with the animals and the creatures, creates their little limestone shells. Those guys die, go to the bottom of the ocean. Then gets kind of pulled in by the plates. So this is a very slow carbon cycle. The quicker carbon cycle is on, involves vegetation, it involves the atmosphere, ocean as well. So one of the ways that CO2 is put into the atmosphere naturally, and the key word here is naturally, is through volcanoes and also hot springs, such as Yellowstone National Park. It requires high heat, which is very familiar to, sounds very familiar when we're talking about cement production. It takes high heat to bust that limestone up chemically to release CO2. But on the other side of this, the way that the Earth gets rid of the CO2 in the atmosphere is chemical weathering. And it's chemical weathering of silica-rich rocks, which removes the CO2 from the atmosphere. This is dissolved into carbonate below ground, where we get these, those formations in the Carlsbad Carlsbad Cavern, I believe, the stalactites and the stalagmites. That's one of the way that the Earth is getting CO2 out of the atmosphere. Another way is the ions from the chemical weathering in the soil. Ions go into the ocean. CO2 is taken again by those lovely little sea creatures to make their shells. So when they die, it goes down into the bottom, and again gets, when the plates converge, it goes into the Earth again. So this is the Earth's way of getting rid of CO2 in the atmosphere. So these all of these processes are, they create feedback loops. So in a warmer climate, we have increased temperature, precipitation, and vegetation, which increases the chemical weathering, which increases CO2 removal, which creates this feedback loop of cooling. Same way in a colder climate, decreased temperature, precipitation, and vegetation decreases the chemical weathering, slows down CO2 removal, and it reduces the cooling. And this is a brilliant, when I first learned this, it was kind of a huge mind blown moment. Mother Earth is really good at taking care of herself when things are going on naturally, I suppose. But what's worrisome is this natural process is clearly not happening quick enough for what we have been doing in the last 150 years. So I'm going to talk a little bit about the correlation between CO2 and the temperature. These data points were originally published in Nature Research Journal, and they were collected in Antarctica in ice cores, and they reconstruct temperature and greenhouse gas concentrations over the last 425 years. As the temperature anomalies, as CO2 levels rise, temperature anomalies rise as well. And this is a pretty cyclical kind of peaks and valleys, which are caused by a lot of things, but for the most part, there are cyclical orbital changes. While this correlation is well documented, temperature changes and climate variability are not only caused by CO2 concentrations. There's several other natural forcings, such as solar activity, volcanic activity and dust, that's a big one. Vapor in the atmosphere, it acts as a greenhouse gas, and this can also affect global temperatures. But the key word here is all of those things are natural. CO2 levels since the Industrial Revolution are not. They're going up way higher than anything our great mother has seen. So we're spewing out now more CO2 into the environment and at a quicker rate than any natural forcing. Since the Industrial Revolution, CO2 levels and temperatures are rising much faster than they did during the last extreme greenhouse climate, which is called the PETM, which stands for Paleo-Eocene Thermal Maximum. It was roughly 55 million years ago and lasted for approximately 100,000 years. This interview was characterized by the highest global temperatures from the Cenozoic era until present. And it took thousands of years for the temperatures to rise this much. We aren't at the levels of CO2 during the PETM yet, but we're headed there very quickly. At the beginning of the last extreme greenhouse climate, the Earth was already relatively warm compared with today's standards, and there were no polar ice caps. Temperatures rose from about 5 degrees to 8 degrees Celsius, making temperatures at the poles 23 degrees Celsius. And the ocean waters were about 20 degrees. This is an extreme warming, which occurred after an extreme release of carbon dioxide, methane, and other greenhouse gases. So one hypothesis for why where these gases came from, it could be, nobody really knows, but it could be that it was a rash of wildfires, could be giant seams of coal were exposed to volcanoes, could have been that mild warming caused methane to be released from under the tundra. Like there's many different reasons that it could have happened, but nobody's really sure as to why. During this period, there is fossil evidence of crocodiles and turtles north of the Arctic Circle, and also ginkgos and ferns and redwoods. During this time, the globe had warmed more than humans had seen up until that point, and it just shows how extreme the effects of climate can be. And it allows for some pretty striking comparisons of the of the kind of direction we're heading with our CO2 emissions. So some projections. The IPCC, which stands for the Intergovernmental Panel on Climate Change, developed a series of scenarios for greenhouse gas emissions. In dark blue, we have actual CO2 emissions, which is a jumping off point for all 4 scenarios. RCP stands for representative concentration pathways. Pink is no mitigation, orange, intermediate, light blue, intermediate again, and the green is stringent, where it actually brings CO2 levels back down. If we do nothing, we're gonna end up somewhere in here. For the climate model that I'm going to show you, I'm looking at intermediate to fairly drastic lowering of CO2 emissions. I'm being hopeful. So we are looking at a climate model now that looks at the difference in average temperature in 2 20-year spans. One is the year 2000 to 2020. And the next is 2080 to 2100. You see around the equator, the changes are relatively small, but at the poles, there's substantial change. In some areas, it's over 5 degrees. And this is primarily due to the polar ice caps melting and creating, and making, so without the polar ice caps, there's less reflection of solar radiation. So it actually increases the warming in those areas even more. So global CO2 emissions by sector, building materials and construction, 11%. And this is put out by Architecture 2030. So it's clearly not as high as transportation or operations, but there's still a lot of room for improvement. So now I'm going to go into some of the solutions. First one I'm going to talk about is geoengineering. But before I get there, we need to have an integrated approach. So this was published in Physics Today back in 2014, and it's comprehensive risk management, where we need to have all 4 of these strategies. So we need mitigation, geoengineering, knowledge-based expansion, and also adaptation if we're going to affect the trajectory of climate change. So geoengineering, I'm not doing this one first because I think it's the most important. It really just kind of is the flow of the presentation. And this is, so I just wanted to get that out there. There's several solutions. So geoengineering solutions, they really need to not negatively affect the Earth systems as a whole. And several solutions are out there. But they vary between efficacy and also feasibility, and also they need to not hurt the Earth as it is. So I mean, there's one of space mirrors, has very questionable efficacy. It's very expensive. Several others are very risky for the environment. I mean, this one here of adding sulfates to the atmosphere to reflect solar radiation. Who knows what adding that to the environment will do. Another one, creating clouds over the ocean to reflect solar radiation. Just sticking clouds out into the ocean. I mean, we have no idea what it's going to do to global weather patterns. It's very risky. Another proposal out there is ocean ion fertilization, right? So they're adding fertilization to kind of the areas in the ocean that are dead zones with no oxygen. We have no idea what that's going to do. Maybe those dead zones are there for a reason. So there's very likely unintended consequences of these strategies. A couple of the strategies that do hold some promise, in my opinion, carbon capture holds some promise, along with afforestation, which is reintroducing forests and leaving them there so that carbon can be stored in the trees and the soil beneath. As trees are cut down, not only are the animal habitats destroyed, but these trees stop taking in CO2, and they also release the CO2 that's been stored underground. So this is an image that I got from the USDA website, and different trees hold in different amounts of carbon in soil. Trees from tropical forests are estimated to hold more than 50% of their carbon in trees, and the other is in the is below them in the soil. The boreal forests in Canada, the trees hold as little as 5% of their carbon, and the rest is all below the surface, as we can see here. This means 95% of the boreal forest stored is locked up in its soils, wetlands and peatlands. Absent of human intervention, this will largely remain there. So another is carbon capture, where seems to have the most promise. It takes CO2 out of the atmosphere and it combines it with oxygen to create a fuel, which is chemically the same as gasoline. So it can not only create fuel for the transportation industry, it can also capture CO2 and solidify it for storage. The Wall Street Journal reported on February 12th, 2020, the Exxon, Mobil, Chevron, and Microsoft Corp and others are focused on reducing the cost. So hopefully this, this group of large corporations working together will make this common practice. So adaptation. We're going to plan for impacts, build for resiliency. You can look on this map. I mean, there's natural disasters that we need to worry about pretty much everywhere in the country. After Superstorm Sandy, I heard this interview on NPR, and it was with insurers, and the only thing they said was we need to build our buildings safer and prepare for eventually what will come. So concrete masonry structures are safer structures. They're resilient to floods and hurricanes, fire and high wind events, and mass walls provide passive thermal performance. So concrete masonry is a FEMA class 5, which is highly resistant to floodwater, and after it's cleaned, it does not hold in harmful pollutants. So here's an image after Hurricane Katrina in Mississippi, where the only building in this neighborhood standing was a concrete structure. Here's Superstorm Sandy. This is my old neighborhood. I used to live in Red Hook, Brooklyn, and after Superstorm Sandy, it just got completely flooded. I knew many people that moved out of New York due to this. Their businesses got flooded, but in this Google Earth image shows the same neighborhood in 2018, and these big old masonry structures allowed these communities to be rebuilt. Without this, people move out and it destroys communities. In fact, this area in Red Hook is even thriving more now. This here is actually a new barbecue joint that showed up on the corner where there's stuff out on the sidewalk. It's very festive. So resistance to fire being non-combustible. CMU walls remain structural under fire conditions. So for good fire resistance, we need balanced design, which utilizes both passive systems, which are non-combustible materials, and also compartmentalization, and also active systems, which is sprinklers. In recent history, fire codes have become more and more dependent on active systems, allowing for structures to be made out of more combustible materials. At the same time, and this is really scary, fuel loads in our living rooms have increased by about 10%, by times 10. This is a UL video put out, and on the left we have a legacy room, which is from about 100 years ago, where all of the furnishings are cotton, wood, and wool. On the right, we have a modern room where it's kind of plastic-based, petroleum-based furnishings, right? Like the cushions in our couches, the rugs. And so this fire test was done. So fire set in the same spot. So up, I'm gonna fast forward this guy if I can. So up around, so I'm gonna fast forward this to 1 minute. Maybe I shouldn't have done that. Okay, so here, by the time it's 1 minute, you notice the fire. You call 911. And by the time we get up to, 2 minutes, the fire department dispatches, right? So here, the fire department is starting to dispatch, and now I'm gonna go to 3 minutes. So the fire department doesn't even leave the station until about 5 minutes, but at So I'm going to stop around here right before 3 minutes. This fire on the right is just really going. And this gas that is coming up from the materials that are being burned is pretty much, fuel in the air, which causes these fires to hit flash point way, way quicker. So I think it's at 3 minutes and 40 is when it hits flash points. And the fire department doesn't even get to the door until, with no traffic, best case scenario, 16 minutes. So if we were to keep watching this video, the modern room flashes at 3.5 minutes, where the legacy room doesn't flash until 29 minutes. So, I mean, this is a really huge difference, and it's something to really think about. Materials have changed, buildings are being made out of different materials, and it's really something to consider. So I'm going to go into passive survivability now, and I'm going to combine this with mitigation and lowering operational carbon, because it's very much intertwined due to thermal mass benefits. So a strategy that's being incorporated into resilient design leverages thermal mass properties of concrete masonry. Following a natural disaster, it may be days or weeks before power is restored to a region. And during this time, the thermal mass properties of concrete masonry help to mitigate temperature swings within a building that's lacking heating and cooling capabilities. So this chart here shows the interior temperature of a mass wall. Exterior temperature is in blue, and it shows how a light frame structure very closely follows what's going on outside. This is called thermal lag, and it's one of the benefits of a structure having thermal mass. So kind of a real world, this is my sister Marsha's garage. It's all masonry structure, single wide. And last week when it was hitting up around 90 in the afternoon, you could go into this garage and it felt immediately 15-degree cooler. So it really kind of shows how thermal mass works. And as a side note, I grew up in a block house, like 100% block, like even the stairs, right? The only wood in there was the beams, and we never needed air conditioning in the summertime, ever. So it's remained really, really cool in the summer. Another passive thermal performance strategy, direct heat gain. So this is from the 2030 palette, where you allow solar radiation to come in through the windows, heating up the wall inside, and that will be released at night for when it's cooler. Another thermal storage wall. So the solar radiation comes in and then actually releases it to the other side of this wall. So mitigation, lowering operational carbon. Mass walls in southern climates are used a lot. It works perfectly in desert climates where it holds, because it's very cold at night, holds in the heat gain during the day and vice versa. In the Northeast and in colder climates, the best use of thermal mass is on the inside of the insulation. It absorbs and stores interior temperatures and minimizes thermal lag. So looking at a kind of code-based version of this, this is out of IECC 2015, informed by ASHRAE, and it is the U factors required for different structures. So metal framed, 0.064, mass wall, 0.09. Now, if we look at two assemblies with the exact same amount of insulation, there's 2 inches of insulation on this steel stud versus a mass wall, this assembly will fail code by 14%. Now, if you look at the exact same amount of insulation with a mass wall, this will exceed the code by 36%. So this provides a much more efficient energy envelope. So durability and lifespan, which is reducing emissions by building durable structures that don't have to be continually replaced. This is a Sears home built in the early 1900s. Sears sold these kind of kits with a block machine. This is how actually my family business got started. One of these little machines I found it up above the block plant. And these structures are over 100 years old. And if you start driving around neighborhoods, you start seeing them everywhere, and they're all in really good shape. And this is before admixtures. This is before all of these kind of different things. And the blocks are holding up really well. Another one, which I saw this in a presentation that was completely unrelated to architecture. It was actually a graphic design presentation. It was about not believing what you see, but it's a common misperception that medieval castles were made of masonry. In reality, most of them were wood. They're just not around anymore. And so much that I couldn't even find one on the Googles. I used this Melissa and Doug play castle. And I guess I'm gonna drop it there. So now we get to the good stuff, or well, maybe not good stuff, but lowering embodied carbon during CMU manufacturing by increasing CO2 sequestration and lowering cement consumption. And yes, this is the good stuff, but it's not the best of the presentation is what I meant by that. And this is kind of funny because I can't see anybody's faces, so I'll just laugh to myself. So back to our strategies, taking into account mitigation and also knowledge-based expansion. So mitigation by lowering embodied carbon by using less cement and increasing atmospheric CO2. And knowledge-based expansion due to the decades of research that we've put into this manufacturing technology development to lower our embodied carbon. So this technology increases the reactivity of cement paste and also other raw materials so that we can use less cement and it still conforms to the strength requirements of ASTM C90. This heightened reactivity increases the rate and efficiency of the carbon sequestration and essentially creating a carbon sink. So this is a typical CMU structure. It is a pretty dense unit, and in blue we see the void structure, but then in red what we see is unreacted cement. And in any given dry cast unit there is an amount of unhydrated cement like this. So what this technology seeks to do is sort of make this cement react at the manufacturing process, during the manufacturing process, because these clusters of unhydrated cement, they kind of form this hard shield around them. So over time, carbon dioxide can't get to them. So this technology looks to break that apart during manufacturing. And so we'll be utilizing that unhydrated cement so we can use less of it. And also this will bring us closer to that kind of 45% sequestration potential because it won't be locked up in the unit. So we can do this without using cement substitutes. And this creates more of a carbon sink with the CMU than it currently does. So these are two identical photos of CMU. One of them has reduced carbon and the other one is standard. Same strength, same performance, and one has around 42% less carbon emissions. So looking at global warming potential and embodied carbon using environmental product declarations. So this here is global warming potential of 3 different mixes. This is a simulated industry average. Now, it is simulated because it uses an industry average mix design, which is a cement to aggregate ratio. It uses our plant data, which is why it's not a true industry average. I did this for my own information, just because I was curious and also to compare, but I do realize it's not a true industry average. And then we have a regular normal weight, and then phase 1 of using this technology is a 10% cement reduction. It brings our global warming potential down by 27%. And this is just from reduction in cement. Now looking at phase 2, and this is where we are at now. We're at 10% cement reduction and 8% sequestration, and this is at 28 days. You can see that it brings it down even more, and this is our current target, 15% reduction with 12% sequestration, which would bring us down to 42% at 28 days. Now, I wanted to talk about this for a minute. These global warming potential numbers are taken off our third-party EPDs, and I wanted to be clear about that. These here are calculated because our PCR does not currently account for carbon sequestration. We calculated these based on our tested sequestration rates, and they're not from a third-party verified EPD, which kind of brings me to the last part of this presentation, which is our product category rules and next version of concrete products PCR showing CO2 sequestration. Currently, I am on the group working with UL Environment, and we are updating the concrete products PCR. This is the concrete products PCR for concrete masonry, adhered veneers if they're dry cast, concrete pavers, and pretty much anything that's dry cast. And we're having language making it possible to include the CO2 sequestration rates in our global warming potential numbers. This is currently in development. The public comment period ended July 15th, I believe. I think next week we have a meeting to discuss all of the public comments, but this should be coming out pretty soon. So we'll be able to show our sequestration in our next round of EPDs. So accounting for these reactions of atmospheric carbon dioxide is going to be justified and follow ISO standards 21930. So this leads me to next steps. We're continually working on getting better. I mean, there's methods for CO2 injection, not only in the mixer, but also in our curing chambers. Working on the continuous improvements using this manufacturing technology to further increase cement reactivity. And with that, I will say thank you. And we can open it up for question period.
Thanks, Heidi, for that look across a bunch of aspects of carbon and especially the relationship to concrete masonry. So as I said at the beginning, we have some time for questions. If folks can type those into the Q&A tool, I'm happy to collect and collate them for Heidi and try and get them answered. And while you're doing that, maybe I'll make a quick remindery plug that to receive credit, please follow the link that's at the top of the chat window to the Google form and enter your name and AIA number or your name and email address to make sure that you get the continuing education credit. Questions? Well, I have one. Well, we're waiting, people are pondering. Heidi, you mentioned about the being somewhere around like 25 or 28% of sequestration, and the theoretical maximum is about that 45% that you showed on the pie chart, the 45% that's a result of the carbon split, not the heat. What do you think is like a realistic practical maximum that we might see as technology continues to improve, as you were talking about in your last few slides? Like, do you think we'll get to that 45 eventually? Like, where is that going?
I don't know. I mean, we would. I mean, seeing the upgrades that we've done just to get where we are, it's been very. There's been a ton of research, and it's been very costly. I mean, I think it's. I don't know if we'd ever get. I mean, 100% perfect. I don't know that we could really get there, but I mean. I think we could get a lot higher than we are, but it does take a lot of work and a lot of changes to our manufacturing process. And it's been very expensive as well to do all of these things. So I know cost is always a factor with this kind of stuff. So I mean, it kind of really depends on market drivers to get as high as we can, but I can't really speculate. I don't think we can really get to that 45, but I think we can get a lot closer than we are.
So there's a question about maybe this edges out of the kind of continuing education, product neutral stuff, and just about the availability of the products. Is this across, commonly across all product lines? And is it available only on special products or particular lines to have this kind of reduced carbon or increased sequestration?
Well, currently we're at the 10% reduction, 8% sequestration at 28 days with gray block. I currently am having architectural units tested for sequestration. So at this time, we can offer it in gray block. I can tell you what sequestration rates will likely be for our architectural units, but I don't actually have testing for that. It's something that I'm working on. It's actually at the lab now. And architectural will have different cement reduction ranges as well. That's going to take a lot more work, because I mean, that's something that it can lead to chippage if we don't do it right. So that's a little bit more not as easy, and it's going to take some more time. But as of right now, we have architecturals that sequester CO2, and we have gray block that we can reduce cement and it sequesters CO2. And the injection can happen, the injection of CO2 into the mixer, that can happen on all of our product lines.
So the next question is related to the four possible strategies to reduce carbon emissions and address climate change that you mentioned. And someone is asking if you could review the mitigation part a little bit and say more about what goes into that one. I don't know if you have to actually go back in the slides or just kind of reiterate it.
Well, I gotta see what
see what you said.
Yeah. Okay, so the mitigation. I mean, we can lower operational carbon by utilizing the thermal mass. So that the building envelope is more efficient and can ultimately use less heating and cooling for the structures. I mean, durability, if we build with durable materials, we don't have to replace them as often, so they will last a lot longer, and that lowers the carbon of the structure if you don't have to continuously replace it. If it floods and you don't have to replace everything. And then mitigation, the lowering embodied carbon with the sequestration and cement consumption, I mean, that falls into mitigation as well.
Cool. So there's a pretty detailed question about possibilities of other admixtures or other content of concrete masonry that might sequester additional carbon, perhaps beyond just the sequestration of the carbon released during the manufacturing process. Have you experimented with any of that, or do you know about any efforts in that direction?
You mean sequestering more than what was given off?
Cool. I think so, yeah. About maybe adding other elements that might do that.
No, I can't really speak to that. I just know that I think it would, depending on what it is, I think it would be unlikely to sequester more than what was given off. I mean, because it's kind of like a reverse chemical reaction. I mean, I suppose I can't really speak to doing more because I haven't really looked into any of that. Okay. What we've been working on is just trying to kind of recapture what was given off when the cement was produced.
Right. A question about specification language that might be possible, and especially to have generic public bids as well, so that people could add and move in this direction with the design intent for a block that does a better job capturing and sequestering the carbon. So is there spec language, and is there a generic specification for this?
Yeah, I mean, we do have spec language, but of course, it's proprietary spec, but then we also have some language that is about performance, and it would be, block sequesters X% and uses, X% less cement. So we do have those in the works right now, to be more of a performance-based spec about sequestration and lowered embodied carbon.
So maybe, is that a thing somebody could reach out to you for directly? Yes. I think on some slide after this, we're going to have your contact information up. So
did I not do that?
A good way to, okay. Not yet, but that's okay.
All right.
There's a good question here, which you and I actually talked about when you were rehearsing this. So I'm going to ask also, and that is that the reaction between unreacted cement with atmospheric carbon dioxide, especially as atmospheric carbon dioxide levels increase because of climate change, that affects the pH of concrete, that increased carbonization could be damaging to reinforcing in ways that the current codes, which have been pretty effective for a couple of decades, did not anticipate. So the question is, has that been studied, this issue about increased corrosion on embedded steel in concrete structures?
Well, I mean, when the steel is embedded in the concrete, like with wet cast, it is actually in that concrete, and from what we saw, it doesn't carbonate down as deeply, and it carbonates much slower. With block, that steel is actually not touching the concrete of the block. So when a block wall is reinforced, the reinforcement goes into the cores, and it's actually wet cast is then poured down, and that's how it's held into place. So this fully carbonated block actually doesn't touch the steel.
So in a way, with the masonry units, what you're saying is it's almost splitting that problem in half, because the block does kind of one job and the grout kind of does the other, if I'm understanding that right.
Mm-hmm.
A question about if there's any recycled content in the standard block and if that's factored into the calculations.
That's an interesting topic. When we did EPDs, I did them on everything. We have about 400 of them, and we had a couple of recycled content blocks, and one of them was a crushed concrete, so it was used as an aggregate, and it actually brought up our global warming potential more. And part of the reason was we had to account for that crushed concrete getting processed, but also it wasn't as good of an aggregate. It wasn't as good quality. So we had to use more cement to keep our strengths the same. So it actually brought our global warming potential up, even though, you know, it's recycled content, which is kind of interesting. We have experimented with, well, I mean, for years and years and years, there was, we used blast furnace slag as a cement replacement. And that, you know, we could replace about 40% of the cement. And that used to come from Pennsylvania when there was, you know, Bethlehem Steel and all these different steel industry was out in Pennsylvania. It's since gone overseas. So it's no longer cheap. It used to be in everything we did, but it costs a lot more money now because it's coming from so far away. But I did do an EPD on that, and it still does bring the global warming potential down. And the problem is it costs a lot more money. So that's kind of a limiting factor with that. Other things we've done, I mean, we've experimented with recycled glass. I'm sure that would bring global warming potential down, but I think that the big thing to think about when we're talking about embodied carbon really is cement content. Like we can replace aggregates, but their impact is relatively small compared to what the cement is. So by looking at all of the EPDs we had and seeing all this effort we were putting into just putting recycled content in the block, we kind of figured that our best bet was working on embodied carbon because that's really where most of the impacts are. And getting EPDs on everything really brought that into focus. So does that answer that one?
Great. It's also that's a terrific answer and a good reminder for me to put a little plug here to everybody that if you're interested in these issues, the ongoing Embodied Carbon 101 series is meeting Mondays this summer. You can find out more information about that on the BSA's website as well. But it really addresses a lot of aspects of the kind of foundational knowledge as well as tools that can be applied in everyday work. So the next event is next Monday, the 3rd at 3. So this issue about EPDs and embodied carbon that Heidi was just describing is pretty great transition to that. I don't see any other active questions right here. So Heidi, maybe you could jump to the next slides that have your contact information on them. If anybody wants to jot that down. And I'll say again, thank you to everybody for coming to this event and for the good questions, and especially to Heidi for this great presentation for all of us.
All right. Awesome. Thank you.
Thank you all.